So hello guys, today we're going to be recording our video for our structure project. So today we have the founder of Success in Bahad, Mr. Navanita with us to discuss about the problems and the projects and also the structural challenges that they face in their company. So I'll go first. Mr. Nava, could you give us a small introduction about your company and also the projects that you guys are working on currently?
So hello guys. So basically, our my company the success. I'm not success. Okay, success neighborhood is actually a startup company under UPM. It is founded in 2023, and we began to commence our operation on 2024. So basically, this company focuses on drone technology, where we customize and build our own drone, and then we'll supply to various industries like agriculture, monitoring, engineering companies, and also healthcare. So this our niche area is on structure of the drone, and our main innovation in our company is designing and developing drone using natural fibers. So especially pineapple leaf fiber. So it's been 2 years since our we started our operation, and one of our key products is 16-liter agriculture drone made up of natural fiber. And other than this structure, we also design our own control system, autonomous control system, which is for industry. And our specialty is we customize in and out the drone according to the industrial's need, including A to Z, everything. So yeah, that's a brief introduction of my company.
Okay, thank you for that introduction. Let me just continue on from where AK started. Well, first off, thank you for giving us your time for being here today. Uh, Based on our project, I just have one simple question. What was the main problem you faced, especially regarding structurally during either manufacturing or prototype or in the real world? So one main problem focusing on anything structurally related.
Okay, since as I mentioned earlier, since my company focuses on natural fiber structures, so the main problem starts with manufacturing. It's manufacturing of the raw materials. Because before this initial at the initial stage we outsourced the material from uh, various suppliers. So the problem was the manufacturing facility of that particular material wasn't much in Malaysia, so we had to import from India all those stuff. So that drastically increases the cost of the raw material. So that was the first problem. And after acquiring the material, this natural fiber, unlike carbon fiber, they are a bit hard to handle because of the stiffness. I would say mainly because of the stiffness. Because when you fabricate using synthetic fibers, especially carbon or glass fibers, the moment that you add epoxy, they are easy to mold. Basically, they can follow the shape of mold, and then they are easy to handle. But natural fiber, unlike the synthetic fiber, they are a bit stiffer. So when the material is stiff, it will be harder to fabricate on a mold that which has complex shapes. So especially when you look at a drone, at the center part, when you look at our initial stages, the drone that we did in the initial stages, they will look simple. they would not look complex, such as DJI's current version of drones and some of the China drones. They look, the shapes look complex, but our material, they are, our design will look very simple, flat with a few curves. That's all. But when times goes by, we learn how to we learn about the property of the material, and we found various method to handle this material so that we could also now we are able to produce more complex shapes and achieve a better result. That's our second problem, I would say. And third problem is this material. They have a high absorbability compared to synthetic fibers, because when you look at the property of natural fibers, especially pulp and karnataka, they have a lower density compared to glass fibers and sort of things. So this is because natural fiber tend to have porous structure. So this structure, when they are exposed to epoxy, they tend to absorb all these epoxies. So this can be good, because when more epoxy has been absorbed, so the better result we might get. Yes, but in terms of cost, they will take up more epoxies. So in industry, costing is very important. We need to keep our costs as low as possible. So they tend to add on more. They require more epoxy or any kind of polymer compared to a synthetic fiber. And when they absorb more epoxies or polymer, they tend to get heavier than a synthetic fiber composite. So that's the problem. Fourth problem will be okay, this mechanical property, I would say, because natural fiber, when we compare to carbon fiber, the strength is lower, obviously. So when we are required to use this material, we need to be creative. So we need to play with other parameters in order to overcome this lack of strength. You know, we want something which has a similar result. So when the mechanical property is lower, we need to go creative in order to overcome the problem. So that's that problem. Hope that answers your question.
Okay, that's really interesting. To follow up what Wasik asked, my question is, from your perspective, what do you think this specific structural problem exists in the first place? Is it because of limitation of material, design tools, or something else?
Okay. But, this the problem that I mentioned just now is basically they all exist because of the material's property itself. So, but in order to satisfy your question, I would say that we found difficult to solve this problem. I mean, in order to compensate the lack of strength, all those small problems, we found it very difficult because of lack of facility, I would say. Because until now, in order to fabricate a drone arm, we still use a basic fabrication method, which is called as hand layup, and also filament winding. So even with this filament winding, if you go into industry, they will use machineries in order to do that fabrication. It will look something similar like a 3D printer. But in our company, still it's a very new company and also a small company, we are doing it manually. So when we do it manually, there are pros and cons. Okay, sometimes if human is involved, the precision is better. The precision is better, but the consistency will be not there. So in fabrication, consistency is very important because no matter how well you do, there will be irregularities among the structures. So that's why composite. That's a downside of composites. But if you use a machine to fabricate, vacuum molding, all those stuff, the result will be better because machines tend to be more consistent compared to human. So I would say lack of facility would be the major reason why we found to overcome these problems.
Right. Thank you, Mr. Nawa, for the info just now, and that was really um, well said, lah. And then for my part, I would like to ask, from the problems that we have discussed just now, how the company overcome those problems.
Okay, in terms of overcoming the problems, in terms of machineries, we are still compensating the usage of machineries with our own skills because when it involves money, you cannot straight away. It's not a multi-million dollar company, no. So in terms of when we are lack of machineries, we still depend on our skills in order to almost compensate the lack of consistency. So apart from that, just now I told about the property. Since we are dealing with natural fibers, the one of the weakness is the property lack of strength. So that's where the engineering theory application comes in because when we first designed our natural fiber drone, it was made up of flat panel, a structure which is flat, a simple design. So what happened was when we are required to build a bigger drone and bigger capacity drone. Initially, it was done for 1.5 kilogram of payload. So the total weight, including every component, will be around 2 kilo maximum, something like that. But as time goes by, we are required to design a drone which can carry 3 kilogram of payload, all those stuff. So when the payload increases, we need to increase the propulsion power as well. So bigger motor, bigger battery. So what happened was, since it was a flat panel, when we fix a bigger motor at the end of the structure, it became bent. It bent. So we also played with the designs, maybe the fabrication method, maybe. So what we did was we tried to achieve the 50-50 ratio of composition, which is really hard when you are doing the fabrication manually. Yeah? Usually the best that we can get is 40-60, 40% of fiber, 40% matrix, and then 60% polymer. That's the best that we could. But we tried to go for 50-50. Well, we're almost there, but still the result was same. So we found that okay, there is something more we need to change in order to overcome this. And then we played with the shape. When there is a sharp edge at the arm will have two ends. One will be fixed end, another one is will be the free end. So we try to change the edge, fix and edge with a curve design because that might help the rigidity of the arm. Still, the arm bended at the free end. So that's when the area moment of inertia comes in. So since we are using a rectangular flat panel, the area moment of inertia is low. So we found that deflection depends on area moment of inertia. So we need some shape to overcome that, to increase the stiffness and reduce the deflection. So we found that area moment of inertia is inversely proportional to deflection. So we tried various shapes, cuboid, hollow cubical rod, and then flat panel, and then triangular panel, and then finally we tried with the circular hollow tube. So among this, all these products, I mean shapes, circular hollow tube is the one that suits our application, and it has the highest area for more moment. So that's when we knew that this can be overcome without missionaries all this advanced fabrication method. Yes, just using engineering theoretical application. So we changed the rods. Instead of using flat panels, we started to use circular panels, and with that we have successfully designed up until a drone which can withstand up to 16 kilogram payload with a total takeoff gross weight around 52 kilos. So that's how we overcome it without much investment on the missionaries. Yes. And also another thing is uh, each time we acquire the raw material, it has it will be not consistent. So what we did was instead of outsourcing the raw material, we set up a production line in order to produce the raw material by ourselves. So when there is a production of raw material by ourselves, we can make the raw material to be consistent. So that's where we control the quality of our product. Yeah.
Okay, thank you, Mr. Nava, on answering everyone's question. So, lastly, I would like to ask about your uh, future suggestions or recommendations on making the success drones a way more better product.
Okay. So our plans are our plans to make it more money is obviously we tried everything using our own, I mean within our own power for now. So as an engineer who is graduated from UPM also, my concept is when we are able to make things by ourselves, why you have to depend on a third party product which is far more expensive. So my plan of doing is I've decided to design my own machine on a filament winding. Yes, it might take a while, but while this can be made based on my preference, customized by myself. So basically, my plan is to create a machine in order to do this filament winding method, so which can increase the quality of a product and also hybridize the material because relying 100% on one type of fiber, for example, natural fiber, limits the quality, limits the property. For example, pineapple leaf has more flexibility compared to canal fiber, but canal fiber has more rigidity. So some application we need the material to be a bit flexible. Some application we need the material to be more rigid. So instead of using it separately, I thought of uh, why not hybridize in order to get the best of both. So these are my plans for now, and currently the best that we could achieve on the drone structure is around 60% of natural fiber. The remaining 40% is made up of aluminium, all the stuff. So in future, near upcoming, I'm planning to achieve 80% of natural fiber. Yeah, so that's my plan for now. and you want recommend. That's your question, right? My plan of moving forward.
Yes, it answers perfectly to my question.
Okay. Any other questions?
I think that's all for now. And thank you so much for answering our questions and giving us your time. We wish you all the best for your future plans. And once again, thank you so much for helping us out with our assignment.
Hmm. Okay, sure, no problem. Thank you for calling me. Hope you all get A for your subject. Okay. Yeah. Okay. Bye bye. Thank you.
Bye.
Goodbye. Thank you.
Thank you, Mr.